Okay, so today's video is actually going to be on the Moore-Penrose pseudo-inverse, but first I need to go recover some lost items. I got absolutely butchered, like ambushed by some pillagers and some like small zombies. So where's my horse? Oh god, is that my horse over there? I think that's my horse over there. Okay, it's kind of laggy though. Yeah, it's probably because I'm recording at the same time. What is he doing all the way over there, bro? Come on. Oh, he probably came up from the platform and walked all the way here. I need to like... Oh god. Yeah, okay. So let's go get our stuff. I'm not even sure it's safe to like leave this horse. This is not even the best horse I've had. I had a better horse than this, but I lost him in the snow. Like somewhere up here we fell into the snow and I just couldn't get out. Okay. Whoopsie daisy. Come on, let's go. I wonder where I'm gonna leave him though. He probably isn't gonna wander too far, right? I don't think so. Yeah, I think it's fine. It's not gonna wander too far. But it's actually a really long walk, so I don't know. I kinda just wanna make this quick, so if I lose the horse, I lose the horse. Let's just go as quickly as we can. Have to be careful around these snowy areas. Okay, so that's my beacon that I set up over there. Let's just go. I'm not sure exactly where I died though, that's the thing. I was so frustrated that I just kind of logged off and I didn't like pay attention. I'm pretty sure I was like walking along, like, where is it? Okay, I was walking along somewhere here, and then I got attacked by some pillagers, and then I fell into a crevice somewhere. I don't know where though, that's the thing. Is it here? It's somewhere, I just like randomly fell, like... Oh god, it's gonna be so hard, like if I have to like start over and get back all my stuff. Come on, I'm pretty sure it's like somewhere close by. Stupid zombie. Like if the zombie wasn't there, I definitely would have survived. And it didn't help that I was like low on like food as well, so I couldn't regenerate my HP because I probably would have killed him with a couple of hits. Oh god, where is that man? Yeah, I think we might just have to like cut our losses there, man. I do have some diamonds in the chest, so I can like at least get back my pickaxe, but oh man, this sucks, because I had so much stuff on me. Was it here? Wait a minute, what is that? Ah! Is that an Enderman? You know what, I'm not even going to... Yeah, nope, I'm not looking at you, dude. Nope, you didn't see that right. Bro, this place is literally cursed, man. I'm telling you, it's cursed. Yeah, I think I give up. I don't think I'm gonna find back where I died. Man, that's so sad. It's so sad. What? What even is that? Why is there lava here? Where am I exactly? I'm getting lost again. Okay, so I think I'm just going to agree to cut my losses here. But I need to get back. Okay, so the snowy mountains over there, so I'm just gonna like... Well, that's a pretty good horse. It looks like a good horse. Let me see if it's better than my current horse, actually. Nope. Okay, we're gone. Alright, we're just gonna log out in a second. Let me just make sure I get my bearings back. Man, it feels so bad. I'm like, my intuition was telling me that I needed to like get the hell out of here, but I just didn't listen. Okay, what did I lose exactly? I lost all my gear. At least I still have my saddle, so that's good. I have the horse, have the saddle. I lost a good amount of iron. Oh my god! No way that just happened. Whoa. So much for the horse and saddle. This just keeps happening to me, like for some reason. How did I not see that? Like, can somebody explain? Look at this, like you cannot make that up. There's so much like mobs like is spawning. It's insane. And they're literally just like, look at them! Bro! No. This is not fair. Come on. You guys got it. Get up. I need help. Help me, please. That's right, run if you know what's good for you. You know what, if I had these dogs with me, I would have been fine. You know what, now I regret not taking them with me, because they probably would have saved me from like that pillager ambush. Man, I'm so dejected right now, because not only did I lose like all of that stuff, I lost my horse. Like, okay, it's so hard to get like a good horse. I'm taking these dogs with me, bro, because I need to get some stuff in order. Okay, we're gonna start the video in a bit, but please let me just get back some stuff, bro. Like, this is too much for me. Okay, what do I need? What can I make? Oh, I don't have enough diamonds for that. I guess the most important thing would probably be the sword, but I do have a gold sword, which is probably like equivalent to the iron sword, so it's fine. I should probably make a shield. The shield will be helpful, I know. How do I make a shield again? I need like iron. Oh god, I don't have iron. Oh jeez Louise. We're in for it. Alright, we'll settle it for the sword and like hope we can like put enough damage on them. Let me put this back. Yeah, but it's looking like I'm gonna have to start over. Like, it really is. Oh crap, let me leave the door open. Okay, let's go. Like, bro, I need to help them. I don't want this guy, like, oh no, I hit my own guy. They're so good though, like, they're so coordinated. I didn't have to do anything. And I'm getting more bones, so this is good. Yeah, I had no idea they were actually that useful. Like, I just had them in the house doing nothing. Okay, let's see what's the best we can do here. What's worse now is I don't even have the horse, so it's gonna be a long trek. Now the question is, do I even remember where I fell? You see, this is what happened to me the last time as well. I was like mindlessly just walking, right? And then I just fell somewhere. I just wasn't paying attention to where I was going, and I just fell somewhere. And like, my mind is telling me like there's no way I'm gonna be falling anywhere so deep, right? But no, it's like really bad. Yeah, it's just really bad. Maybe I just like logged into a really cursed world, because it's nice, right? It's really nice where I spawned, but like maybe this is the cost you pay for niceness. No. Okay, let's just get up. Let's get back the horse, and I'm happy, right? This is like gambling, you know, like with gambling you lose, right? And then you just say, oh, you know, I'll just make back my loss, and then you just keep losing more. This is exactly what's happening right now. Watch me lose all 3 of these. Wait, weren't there 3 of them? Oh, here he is. Yeah, watch me lose all 3 of my wolves, just because I want to get back my horse. And I lost the horse because I just wanted to get back my... Oh god. Here's the thing though, I don't know where I fell. That's the really sad part. Where did I fall? Maybe the horse is smart. Maybe the horse survived, right? And like he like walked out somewhere. Maybe that, let's take hope for that case. Was it I feel like it's somewhere here. There's no way. Was it down here? I swear to god if it's... Oh my god, look at that. How in God's name am I getting the horse out of there? No way, dude. I should have walked with like wood or something. Like the poor horse is like trying to get out, bro, but he can't. Wait, what's going on? Okay, so maybe I'll have to like construct something to like get down there. Let me think. What do I have? I don't have anything. Man, this is just terrible. This is horrible. This is just atrociously bad. Okay, but at least I know where the horse is, so it's next to this like blue flower here. Alright, so I'm gonna have to farm. So my plan of action is I'm gonna like farm a bunch of wood, and then I'm gonna build a staircase coming down. Yeah, I'm gonna have to build it in such a way that I can get the horse out. Oh, this is insane. How did I even fall in here, bro? Like, come on. Oh, look at how deep this cave is. Do you know that infinity castle meme where you're digging down in Minecraft and then you just fall? This is exactly what that is. Why is it so deep? There's this other cave I need to show you where there's like an ancient city, I think, or something, which is just insane. Anyways, okay, fine. I'll have to come back in my own spare time and try to recover this horse. But man, this is just really, really sad. Okay, so let me just I guess save and quit here. But I'm not going anywhere without these wolves, bro. It's too dangerous out here now. Okay, so let's quit and let's go to what we were supposed to be doing. Yep, nobody saw that. Okay, Moore-Penrose pseudo-inverse, right? Yeah, that's really good introduction to a linear algebra video. So let me spell this out. Moore-Penrose pseudo-inverse. I'm not gonna spell it pseudo-inverse, but okay, I'm guessing you can spell inverse, right? So we've already met this before, ax equals b, right? We've seen this before, and we've seen the case where there's no solution, right? So if it's outside of the column space of the matrix, we project and we find best possible. And we've already been over all of this inside of our projection chapter. In this case, right, we'd say that the system is over-determined, right? And there's also the other case where you have infinitely many solutions, right? So your system is over-determined in one case, and then in the other case you have infinitely many solutions. This would be, for instance, you have full row rank, right? But there's something in the null space of your matrix, right? And so in this particular example, then you would say that it's underdetermined. So you have overdetermined systems and you have underdetermined systems. And what we would want in this particular case is the x, right, with the smallest norm, or the smallest length, right? And in essence, the pseudo-inverse, we call this a plus, right? The pseudo-inverse a plus gives you the least squares minimum norm solution to any system ax equals b, right? Because we were talking before about what do you do, right? We were talking about left inverse or right inverse, and what do you do in the case of full column rank, full row rank, and now this is the most general case, right? You don't have full column rank, or you don't have full row rank either, right? You have neither of those things. So that's where you have this pseudo inverse. So you try to get the best of both worlds, right? And that turns out to be a least squares, right? Because ax fundamentally is a column space problem, and then if so, you can either post multiply or pre multiply. So we've seen column operations and we've seen row operations. And okay, we'll clarify this in a bit if it's still unclear. But that's what this a plus mean, and the plus just denotes a pseudo-inverse, right? And so the Moore-Penrose pseudo-inverse has 4 primary axioms that we're working on there. And the first one is a plus a is equal to a, right? This is the first one. We'll get to what this means in a second. The second one would be a plus. Remember, a plus just means inverse, right? Instead of like the minus, you use a plus sign to denote well, it's pseudo-inverse and not a true inverse. This is the second one. Is equal to a plus. The third axiom is simply a plus Hermitian. I hope you remember what Hermitian meant, right? Is equal to a plus. So it's symmetric Hermitian, right? Pay close attention to that. Symmetry here is like super important. And the Hermitian property is just accounting for complex numbers as well. And okay, it's fine if you don't understand anything at this point. We're gonna clear up some things, which I just want to get these axioms out of the way. A plus a, great. And so, right, you should know Hermitian just means the conjugate transpose, right? So, okay, that's fairly simple. We've been over this in our fast Fourier chapter, so I don't want to go over that anymore. And so let's contrast these 4 axioms against the true inverse, right? And so the true inverse would be this, right? You have a, right? A inverse a will give you back a, right? Well, this is fairly straightforward, right? If you put these two together, you're going to get the identity a equals a, fine, right? Nothing strange going on there. And you can like contrast them to see what's going on, right? Like this guy together gives you the identity, you get back a. But we're going to go over that in a bit more depth. what that means exactly, but it's very, very close to the true inverse. And then if you had A inverse, you're going to get A inverse, right? Right, so this gives you the identity, and then identity times A inverse is going to give you back A inverse. And you'll see that this is exactly the same thing we have here, right? So I'm just giving you something to contrast. Now conditions 3 and 4 is where it gets a bit different. If you have A inverse, right, you just get the identity, and then you have A inverse, a left inverse now. You also get the identity. Now it's different in this particular case. So the genius, right, of the Moore-Penrose pseudo-inverse is that they've relaxed these conditions from the identity to being symmetric Hermitian. Alright. Now we need to go a bit more in depth. So let's read page after. So now you know like what the axioms are and the formal definition of the Moore-Penrose pseudo-inverse, but what do these things even mean, right? So let's go dig a little bit deeper. And so let's look at the first axiom, right? And this is actually called the forward solution. And so A times A transpose A is equal to A, right? This is called the forward solution. I'm just going to write FS for short. And so if I did A times X, right, for instance, like if I did A times X, right, then A inverse AX, right, and then after this I did A times A inverse AX, right, what happens, right? It's the same thing as if I just applied A in the first place. Maybe I can show you this like a bit more geometrically. So if I did AX, right, so we're over here now, right, so we're going from one space into another space, and then we came back, right, with A inverse. So we did AX, right, and then we did A inverse. It's going to take us back, right, and then we did A again, right, and so it's going to take us back here. So can you see, like we went, we came back, and we went again. And so this is the same thing as if we just applied A alone. Okay, so I hope that was fairly straightforward, and this just ensures that A inverse can sort of reverse the action of A for all vectors in the column space of the matrix, right? So anything A times X, anytime you see A times X, right, you're dealing with the column space of a matrix. Okay, and so we've got that. Let's see what's over here. Alright, yeah, so mirror image, fairly simple stuff. I can't believe this, but I actually have 3 entire books. I have 3 books of linear algebra, like linear algebra notes, which is insane. Like, why do I have so much linear algebra notes? It's crazy. But it's good because you can always like come back and review stuff. So it's really, really nice. Anyway, so I'm sharing my notes with you guys now. So, okay, condition 2 is what's called the reverse solution. I actually remember this too. So if you had A plus, right, you get A plus. So what is this saying now? This is basically the exact mirror condition of what we just had, right? So you start with instead of like over on this side on the input space, you start on the output space, right? And then you apply A, which should take you back to the input space, right? And then you apply A plus again, and that's going to take you back to where you started. So it's quite literally just the same thing. So it's the same as if you had just applied this one time. So it's fine. Conditions 3 and 4 require a bit more thought, right? So this sort of just, conditions 1 and 2 sort of just establishes a bit of symmetry. You'll see this word symmetry being used quite a bit. So let's go back. Conditions 3 and 4, we need to establish that we're dealing with a projection matrix, right? So I have this meme that I put in my last video, like, what was it? Has it always just been projection matrices? It always has been. I think I put it in the thumbnail of the video, but it really is just projection matrices. Once you understand this idea of projections really, really deeply, then it becomes natural to see what's going on here. And so what is the condition for a projection matrix, right? And so it's just P squared is equal to P, meaning that if I project a matrix once, right, and then I project it again, it's going to stay exactly where it is, right? For instance, if I had this subspace here, and I projected this vector V down into the subspace, it will land at a point P, right? And then if I project it again, we're going to stay in place because we're already where we need to be, right? And so that's the condition on a projection matrix. So this is like an important condition, right? So in other words, we're saying that P, right, P is equal to A times A plus. And we need to show then that this is actually a projection matrix, right? We need to show that this statement here is a projection matrix, and that has to deal with condition 3, right? Where's condition 3? Somewhere up here, AA plus, right? So that's condition 3. So we want to show that this AA plus business is in fact a projection matrix, and so we just need to show then that it's p squared equal to p, right? And then it satisfies the condition. So how would we go about doing this? Well, it's quite simple. You just go A plus times A plus, right? And we need to get A plus back. Okay, and then you can see like why this is fairly simple, because we've just got the pseudo inverse sitting right next to each other here. But that's one way to look at it. That's like the low level way I'm supposed to look at it. There's a better way to look at this, and I believe it's from condition 2, right? So condition 2 is, where's condition 2? Yes, so the reverse condition, right? If you look very carefully here, it's the same thing as the reverse condition, right? So we said, so we can just say this is A plus. So yes, A times itself, A plus times itself is going to give you back this here, right? Because we said this entire thing here is just A plus. And we showed why from the reverse condition, the reverse solution. Okay, so we've established that this thing here that we're dealing with is a projection matrix, right? This AA plus business that's inside of the Moore-Penrose axioms. And so let's show the same thing for the other case as well, which is A plus A. So this one came from condition 4, right? And so we just need to show then that A plus A times A plus A is equal to A plus A, right? We need to show that this is a projection matrix, and then you can quite literally just look at this and apply the same rule again, right? The reverse solution. So this is A plus, and we're good to go. So we are in fact working with projection matrices, if you weren't convinced, right? So insert page. Now, conditions 3 and 4 are also enforcing symmetry, right? So not only are we dealing with projection matrices, we're dealing with symmetric projection matrices. And this, or Hermitian, in this case they're Hermitian, right? Because we're also allowing for complex numbers. Now this P transpose P business, right, is very important. It's like so fundamental to understanding what's going on. And we've already seen like what Hermitian means, so I'm not going to like explain why it's, we're just going to use transpose now, but it's actually P Hermitian equals P Hermitian, but we're going to use a transpose for simplicity in this case, but it's quite literally just the same thing. We're dealing with symmetric matrices. And so we need to show, right, that why are we enforcing this condition? So these are sort of questions you need to be asking yourself, right? Why did they enforce this symmetric condition? So what does it mean, right? So let's say we had this A transpose E. A transpose E. I hope you remember this from our projection chapter. A little more specifically, the least squares chapter. This would just be A transpose, right? B minus PB, right? So A times your error vector, and your error vector is just B minus the projection, right? So, okay, that's fair enough. And so this would just be A transpose B minus A transpose PB, okay? And the portion of interest that we care about is actually this expression here, A transpose B. Now this is not trivial to show at all. It does require quite a bit of thinking. At least from my part back then, it took me quite a while to figure out what was going on here. And so we've already established then that our projection matrix is A transpose in this particular case, right? And especially when you're dealing with column space projections, right? This being on the right hand side indicates that we're dealing with a column operation. If it were on the left hand side, then we're dealing with a row operation, right? And so you should be familiar already. This is fundamental, linear combination of columns as opposed to linear combination of rows. So here we're working with the column space. If it were on the left hand side, we'd be working with the row space. Okay, so P transpose P, right? So we need to show P transpose P. What is this? So this would just be A, right? A transpose, well, A inverse, or A pseudo inverse, I'm gonna call it. We'll say A plus, right? Transpose. Okay, so this is P transpose P. can you see like why this is the case though? Like all we did, right, was transpose this guy, right? So this guy is just been transposed. Okay, so what is this equal to though? Right, this is actually a plus, right? Right, so this is P transpose equals P. I hope you're seeing that here. P transpose equals P. Right, fair enough. And we know then that we can take this transpose, right? We have a product here. Its transpose is going to come in the reverse order, so this is going to be A plus transpose times A transpose, like so. Oops. Well, I'm just going to write the A transpose normally like this. Right, so these three expressions are actually equivalent to each other. And what we want to prove, right, is A transpose P. A transpose P is actually just A transpose, right? A transpose, right? So this is A transpose, this is P, this is literally the P portion, is equal to A transpose. There we go. Okay, so I think we're on our way. So this is what we want to show. So this is P, this is our projection matrix, so we want to show A transpose P is equal to A transpose. Why do we want to show that? If we can show, right, that this A transpose P business is in fact equal to A transpose, then if you come back here, right, if you come back all the way here, look at this, remember this is our portion of interest, right? If we can show that, then we can write A transpose B here, and we'll see that A transpose B minus A transpose B is just 0, right? And the entire point is that we want to prove that having a symmetric projection matrix is going to force an orthogonal projection, right? Not an oblique projection, an orthogonal projection. And you'll see why it's very important that we have an orthogonal projection. Okay, so far we've established this, and we want to show that this is in fact the case, right? And so to show this is actually quite simple. You just go back to condition 1, the forward solution. So you can say A plus A is equal to A, like we've shown this before. If you started with A, take its inverse, right? So, and then apply A again, you end up with A in the first place. Now what you do, right, is transpose this expression here. And so what you end up with is A times A plus times A transpose this is equal to A transpose, right? Because we're trying to get an expression for A transpose, right? And this is like exactly the natural thing to do, right? And if you look very, very carefully here, right, you can take this as a product, right? And it's going to come in reverse order, and so we'll get A transpose, A plus transpose, and then A transpose here equals to A transpose. There we go. And we have exactly what we need. Like I hope you're starting to see like what this is here. This portion we've already met before, and this is simply, right, A transpose A transpose. Like where does this come from? So let's take a look up here. Here it is, where we had those three expressions and we said they were equal to each other. So it's this guy here, right? It's this guy right here. So can you see the A plus transpose A right here? A plus transpose A, here it is, A plus transpose A. And we said, right, that's equivalent to A plus. Okay, so I hope that's clear. Is this A plus or A transpose? I need to be very careful here. It's A plus, so I should be very, very careful. Good. So, right, this is A. Oops. Let me get my eraser. There we go. Right. So we said this was equivalent to what we had up there, right? And so this is actually just equal to A transpose. Okay, so I hope I made that pretty clear what's going on here. So we got the A transpose, which, so this portion here, let me put it in in blue, let me surround it in blue, this portion here collapsed, right, into AA transpose. We said that they were equal to each other, and we proved that up here, right, with P transpose P. We showed that up here, that they're quite literally the same thing, so we just substituted it back in here. It's not a big deal, right? And the point is, right, that we can do A transpose A transpose A plus, right, is equal to A transpose. So do you see like what's happening here? So now we've shown, right, we've quite literally shown what we were looking to do. Where is it here? And we're showing that A transpose P, right, A transpose P is equal to A transpose. That's what we were trying to show in the first place. See? I hope you see that here. This expression here and this expression here are the same thing. I know this was like a little bit messy to follow, maybe, I'm not sure, but I tried my best to maybe try to lay out the steps logically. And so, right, so we know this expression is equal to A transpose. Oops, let me get some water. Okay, now the point is, the entire point is that we were looking at this portion of interest. Where is it? Portion of interest, where are you? I can't seem to find it for some reason. Oh, here it is, right. So our portion of interest here, we can quite literally just substitute in for A transpose P, we can substitute in just A transpose, right? And we'll end up with, well, A transpose B minus A transpose B, and it's going to be 0. And you should know then, well, this shows that having an asymmetric projection matrix will force, right, quite literally force an orthogonal projection, and you see it happening right here in front of you. And I think that's such a nice thing to know. And so A transpose A Hermitian equals to A transpose A is a row operation. So this is for the fourth one, right? And so you have a minimum norm solution. So it's the shortest path from the origin to the solution space. And in this particular case, we're dealing with least squares. We're projecting, right? Since we're applying from the column space, we're projecting down, right? That we're projecting our vector down into the column space. And since it's an orthogonal projection, right? Because we're dealing with a symmetric matrix, so we're forcing an orthogonal projection. We're going to get the closest point, right, to the solution space. Like, I hope that's like clear what I mean by that. Let me get a new page. Okay, so I've shown like condition tree. Condition 4 follows like the same, pretty much the same logic, but this time instead of dealing with the column space, we're dealing with the row space, right? And that is also symmetric. And so again, you're dealing with an orthogonal projection, right? And so the projection path E, right, that's your error vector, is orthogonal to the column space of A. We've seen that. Therefore, it's the closest point in the column space to B. Like, this is fairly simple, right? And the symmetry of A plus A means that an orthogonal projection from the row space, right, you're getting an orthogonal projection onto the row space if you're multiplying on the left. And so A plus B, right, the pseudo-inverse on B doesn't have a null space component. Right? If you had x, right, you had ax is equal to b, right? And then you did this guy here, a plus ax, then, okay, right? So x hat is equal to a plus b. Just make that a little bit more explicit. So there is no null space component now. Right? And what you end up with then is the minimum norm. I hope you know what the norm is. The norm is just the length of the vector, right? So we're looking for the shortest length from the origin. And so in both cases, right, symmetry forces an orthogonal projection, which results, right, by definition, you can see it. You can quite literally see why an orthogonal projection would give you the shortest distance. And so for the case of A plus, right, for the case of A plus, we get the shortest path from B, or vector B, to the column space of A, right, fair enough. And then in the case of the row space, when we're projecting onto the row space, what you get is the shortest path from the origin to your solution set, right? So from your origin to your solution set. Now, this is like so nice, because this is like sort of where everything sort of comes together. It's really, really nice, actually. Like, come on. Anyways, so I hope I didn't do too terrible of a job. Maybe we should just do a very quick recap. We started off with Moore-Penrose pseudo-inverse, ax equals b. This is the solution that we're solving. Okay, we don't have a solution, or we have infinitely many solutions, right? Our system is like underdetermined, overdetermined. There's like, it's not full column rank, it's not full row rank, right? So we have to try and find a pseudo-inverse. And we said there were these 4 axioms, right? This one we called the forward solution, this one we called the reverse solution. You can quite literally see, right? We start with A, we take its inverse, right? So we start at some place, we go back, and then we go forward again, right? So we end up exactly where we started, at A, and then this is quite literally the mirror case, right? So fair enough. Now this was the important bit here, and we said that A multiplied by its pseudo-inverse Hermitian, right? So transpose conjugate is equal to A multiplied by its pseudo-inverse, and that quite literally just means it's a symmetric matrix, and in this case symmetric Hermitian matrix to allow for complex numbers. In this particular instance, this pseudo-inverse showing up on the right means that you're projecting onto the column space. Your pseudo-inverse showing up on the left means you're projecting onto the row space. Right, and then we just, what was this? Okay, yeah, this was the sort of an analogy towards the true inverse to show you that, okay, well, these two are quite trivial, right? And so you see the analogous version in the Moore-Penrose pseudo-inverse. And down here, now, these two conditions are actually relaxed, right? So instead of giving us the identity, right? Because you can't get the identity, obviously, but you can get the best possible. You can get the best possible projection, right, onto that column space, and you can get the minimum norm. And so that's why I said at the very beginning, the Moore-Penrose pseudo-inverse really is the least squares minimum norm solution to your system. And why is that the case? Because these projection matrices, and we showed, right, we showed why this A plus business and this A plus A business was a projection matrix, right? We showed p squared equals p, and then we also showed what it meant if they were symmetric, right? So p transpose equals p. And we saw then that if we had a symmetric projection matrix, it automatically meant, right, that this A transpose p portion turned into A transpose, right? And then we got A transpose b minus A transpose b. And okay, we had like a little bit of juggling around to do here using the forward and reverse axioms, and we showed, right, that this is in fact the case. Having a symmetric projection matrix is going to give you an orthogonal projection. In fact, if they weren't symmetric, right, you would get an oblique projection, which is, oh god, is exactly what you do not want in this case. But okay, and this is like the genius of like the Moore-Penrose pseudo-inverse, as opposed to some other like a quote-unquote generalized pseudo-inverses out there. Okay, so now let's talk about like what the actual meaning of this is, right? And so we said before, A can be decomposed into an orthogonal matrix U, a diagonal matrix sigma, and another orthogonal matrix V transpose, right? And now A plus now is just going to be this guy, right? So we want to get rid of whatever is here, and so to do that you would need to put a V transpose here, right? Oh, sorry, not a V transpose, just a V here to knock out this V, right? To give you the identity here, right? You would need this sigma pseudo inverse, whatever this is. We don't know what this is as yet, and then you would need a U transpose here, right? This is what you need to get rid of this. So this portion is going to go and turn into, you know, identity. This is going to go, and then this is going to go, right? And that would leave you with your A inverse. And so A plus then is quite literally just V sigma plus U transpose. Now the part we haven't really spoken about is what is this a sigma plus, right? What is the pseudo inverse of this sigma guy here? Remember before we said sigma was just a diagonal matrix, right? So zeros all over like here, and then we had these eigenvalues sitting right on the diagonal. Remember the eigenvalues were for A transpose A transpose, right? Now the really nice part is that since we have a diagonal matrix, we can very easily know what the inverse of this matrix is, right? It's just 1 over the sigmas. That's it, right? So if you divide, right, if you multiply by 1 over the sigmas, you're going to get the inverse of this matrix. By definition, that's the multiplicative inverse, right? And so what you're going to end up with is like 1 over sigma 1, 1 over sigma 2, all the way up to n, right? Then you have your zeros, sigma n, and you're good to go. And that's what sigma plus is. So you've managed, right, to decouple all the really, really messy parts of your matrix into this diagonal sigma that's really easy to compute the pseudo-inverse for, right? You just put 1 over, right? And you're done. Because V is an orthogonal, an orthonormal, right? It had an orthonormal basis, right? So V and U, we can just like go Q transpose Q, right? They're orthogonal matrices, so that's really nice. So we can very easily compute their inverses. Okay, and so that's the entire point of the Moore-Penrose pseudo-inverse. Now, I can't help but think that I'm forgetting something here. Oh, that's right. So the we actually haven't spoken as to how you would compute the pseudo-inverse. So let me see if I have any notes on this. I'm certain I do, but I'm not sure where I have them. I'm not sure where I have them at all. Oh, right. So, okay. But I do have like a general inkling of where I should go from here. Okay, let's just get a new page after. Okay. So the last time, right, we were talking about singular value decomposition, and we said before that we had some orthogonal pair of vectors in the row space, right? And we did some linear transformation A, and we ended up with an orthogonal pair of vectors in the column space. And we kind of wanted to show, like, why is it, I said like this wasn't entirely obvious, right? So we need to show that that is in fact the case, right? So, okay, we know then that AV1, right, AV1 is equal to sigma 1 U1. Like, okay, we've seen this before, right? And AV2 is just sigma 2 U2. Okay. And once we've managed to solve for the V's, right, we can very easily solve for the U's, right? We can just do some simple transposition. We'll get U1 is equal to AV1 over sigma 1, and U2 is equal to AV2 up to sigma 2. And then you can just generalize, right? It's not a big deal. And the point is, why does an orthogonal pair of vectors in a row space come out as an orthogonal pair in U, right? So what we need to show, right, is U1 transpose U2 is equal to 0. Like, this is the test for orthogonality, right? Okay, so we obviously need to start with what we know. So this is just AV1 transpose, right? Let me just write the entire thing out. So it's AV1 divided by sigma 1, this entire thing transposed, multiplied by U2, which is just AV2 over sigma 2, right? And we need to show that this is equal to 0. Now, the point here, right, is, okay, we can, like, distribute this transpose in here, and so we're just going to get V1 transpose, A transpose, right, times AV2, and then, okay, we can just multiply this sigma 1 and sigma 2 together. This is just basic algebra. Now, the really, really nice part here is that this AV2, right, is equivalent to sigma 2 V2. Can you see that? Okay, I wrote theta 2, but this is actually sigma 2 V2. Right? Can you see this? This should be fairly straightforward, right? It's sitting right there, right? Come on, it's sitting right there. Like, and we've seen this before, right? We've seen this before. It's an eigenvector, and this is the eigenvalues. So, and this is like the really nice part. And so it's not just, it's sigma squared 2 times V2. It's sigma squared 2 times V2. So this portion here, so my apologies there for leaving out the squared. I hope you remember that's when we had AV is equal to sigma, right, times V, sigma squared times V. And then if we like multiply by the transpose, then we would be good to go. Or was this, I think it was, hang on a second. I just don't want to get this wrong, so I believe it's this, actually. it should be v times the sigma here, yeah. And so that way when you multiply by the transpose, right, so then you would just get v sigma squared v transpose over here, and that's like exactly the solution that we've met with before. So I think this is correct, but because in this particular case here we're dealing, we know that sigma squared is just a scalar value, so we can actually just move it around in this particular case. So the order doesn't matter. I could put this sigma squared over here, I could put it over here. Since it's a scalar, right, we can do that. It's commutative in that case. But regular matrix multiplication is by no means commutative. But by this time, if you've made it this far into linear algebra, you should know this. But okay, so we can just do like a little bit of substitution here, right? And so what we end up with is v transpose sigma. Why do I keep writing theta? Come on. Sigma, here we go. Sigma 2 v2 divided by sigma 1. And remember we had a sigma 2 here, so we canceled this with the square we had up here, right? I hope you see what that is. Okay. And what this implies, okay, my notes are messy, but what this implies here is, okay, we can drag out the sigma 2's and the sigma 1's, right? So we'll get sigma 2 over sigma 1. I keep writing theta over, yeah, but it's a bit hard because I have like a really trashy mouse, right? Multiplied by v1 transpose v2. Okay, and you should see that, okay, these two vectors here are in fact orthogonal, and so when you take their product like this, x transpose y for instance, but in this case it's just v1 v2, v1 transpose v2, then yes, of course it's going to go to 0, and so we can see the entire expression in fact goes to 0. And so we've managed to prove our initial case then that yes, somehow these two vectors u1 transpose and then u2 come out to be, like u1 and u2 come out to be orthogonal to each other. So that's like by no means a trivial thing, right? It's a very important result actually. And so we've seen before then that, let's go to the next page. We've seen before, so A is equal to u sigma v transpose, and so the really nice way to see this, right, is that you can break this matrix up into a sum of rank 1 matrices. And so this is like the same thing as sigma 1 u1 v1 plus, you know, sigma 2 u2 v2. What does this look like though? So you have your, okay, so it looks like this. Your u1, your sigma 1, your v1 like this. It looks like this, right? And then it would be the same thing here as well. So it really is just a sum of rank 1 matrices. Okay, this is like the really nice way to look at this, and by convention these sigmas are ordered by importance as well, and so you'll see that later on. And this actually allows you to introduce a really neat idea known as tensor decomposition, right? And so now instead of working with just two orthogonal pair of vectors, right, suppose you had an entire basis, right, for a tensor, and you should know, like, you had a matrix, right? So your matrix just looks like this, and you can say this is like a one-dimensional matrix, right, in a sense, right? But then you can extend it outwards like this. You can extend it outward into a cube, right? And so it's like a collection of matrices, right? It's a multi-dimensional array, if you want to think of it that way. And in essence, that's what a tensor is. Funny story, I actually remember I had some project back really early on. I had a project, I think it was year 1 or something. We had like some project we had to do, man, and I used the tensor decomposition in that project. I think we failed the project. I was like, come on, man, like I did some really heavy math in this project. We literally just failed, bro. It was so funny. I'm not sure what happened. I think we still got an A for the course, but we literally just failed that project. It was so funny. I didn't even care because, like, you know, I don't really care that much about grades, to be honest with you. I just want to learn. I'm just interested in learning. I don't think grades at all reflect your capabilities in any way. And I think that project was like a pristine example, really. Anyways, I'm proud of that project, by the way. I'm very proud of that project. That project took some life out of me for sure. Anyways, back to our tensor decomposition. And so we can write this as, like, for instance, sigma 1 and we can have like a multi-dimensional aspect to this. Like, I hope you can see like what's going on here. So now instead of just u1 and v1, we can have another basis as well. We can call it w, or call it whatever the hell you want to call it, right? And you can see this idea will decompose, and so these are all orthogonal pairs, right? Okay, so u2, and then I'll just draw in like one more here. Like, I know the drawing is terrible. I'm doing my best here. I'm sorry. But here we go. So it's like a sum of like rank 1 matrices, and like you put it together and you'll reconstruct your tensor, right? Or in this case, in the two-dimensional case, it's quite easy to see as well. You'll be able to reconstruct your tensor. Okay, and so we need to show why is sigma a diagonal matrix. I think this is important to know as well. It's not trivial, right, at all, really. So we said sigma before is equal to like this u1 transpose all the way up to um transpose. This is what sigma is. All we're doing here, we've rearranged our original singular value decomposition to solve for sigma. And so we'll get a v1 all the way up to a vn, like so, right? So I'll just like show you very quickly what it is. So we had u sigma v transpose, right? And then av is just u sigma, and then, okay, you can see that u transpose AV is equal to sigma, right? And this is where this equation came from. I know sometimes I tend to work backwards, which is a bit weird, but okay. Sorry, I didn't start with this and then go to this. Somehow I started with this and then came to this, which is fine. And then you can see then by matrix multiplication, right? This is just AV1, right? You're taking linear combinations now, so AV1 times, so it'll be U1 AV1, right? So this, I'll put the solution here, so it'll just be U1 transpose, sorry, times AV1. It's U1 transpose. Very, very important, that transpose right there. Makes all the difference, actually. U2 transpose times AV1, right? So it's AV1 comes here, right, multiplies all this entire thing, and then all the way down to AVN, right? So you just count upwards. And the point is, right, oh, and this matrix, by the way, is m by n. You should know that by now. And the point is, right, that these value here, or these values that are off your main diagonals, are all going to go to 0. And can you see why? Because they're orthogonal to each other. Like, I hope you see that they're orthogonal to each other, and so that's why they're going to go to 0, right? So a times v1 is going to produce some other u2, right? That's quite literally orthogonal to v1, right? So I don't know if you're seeing that, but it should be like clear to you, right? Because we started with v1 v2, an orthogonal pair, right? And we ended up with u1 u2, another orthogonal pair. So it makes sense that then v1, right, is going to be orthogonal to u2 transpose. Yes, of course. Alright. So let me not labor that point any further, and then obviously you'll end up with the correct values that you're supposed to get here on your main diagonals. So you're good to go there. Okay, let me see. Is there anything else useful that I can... Oh, right. How to compute the singular value. Oh my god. I should have started with this. I should have started with how to compute, because that's where we left off the last time. But okay, it's fine that we end here as well, which is, it's okay. Okay, how do you do this singular value decomposition, right? So before, right, we said that if you had A is equal to U sigma V transpose, right? And it would depend, so you would have to do for like left multiply or post multiply by the transpose, right? And we've already seen what this means in a lot of different contexts. You're either doing row operation or you're doing a column operation, right? And we've seen that this is not the correct way, and so you use that, so you can actually go A times A transpose, right? And then you can solve, and so this would just be U sigma V transpose, right? So this is A, and then A transpose would just be, A transpose would come in the reverse order, right? I hope you can see that. So we've already been over this like many times before, but the point is we're going to end up with V sigma transpose U transpose, right? The V's are going to go, and you're going to end up with U sigma squared U transpose. transpose, like this, right? And well, obviously then we know then the U's are going to be the eigenvectors of A transpose, right? And the sigmas are just going to be your eigenvalues squared. Of course, you're going to have, if you want the singular values, you're going to have to take the square root of that. So it's fairly simple, right? And then once you have the U's, you can find the V's, or conversely, if you wanted to do this the other way, if you wanted to do A transpose A instead of A transpose, which I think is the more sensible thing to do, to be honest with you, because A transpose A, right, is going to come out n by n, and A transpose is going to come out m by n, right? So one is obviously bigger than the other one, and the point is that you're going to have n. You're going to end up with n of these sigmas, right? If you did so, like by convention, like if you were doing it this way, you would do A transpose A, and you would have n of these sigmas, right, sitting on your diagonal. And it turns out, right, that for A transpose, when you're solving, now let's go up here somewhere. I had that equation, right? So when if you want to solve for u1 up to um, right, then you would just divide by AV1 divided by sigma 1 all the way up to sigma n, and then all the other values will turn out to be zeros. And you do need to do a numerical example, I think, to see that. But this is like the naive way to compute this, right? So we have to use, we could find the V's, or we could just say A transpose A, like this. Right, in this particular case, it's again, we had U sigma V transpose, so I'm just like trying to take my time and go this over now. And in this particular case, you would just end up with, let me just put this down here, you would end up with V sigma U transpose, and the U's would go, the sigmas would go, well, the sigma squared, you'll get sigma squared, and you'll get V sigma squared V transpose, right? And now you have this, right? Then you're okay, you're pretty much set, right? And what do you do from here? Then you have to solve, right, your characteristic polynomial, and this is where it becomes a nightmare. So you'll have to solve A transpose A minus lambda I x equals 0, and so you'll take the determinant of this thing, and now you can see, right, if you had a really large matrix, you're going to end up with a nightmare polynomial to solve, right? Good luck solving that thing, right? It's horrible, it's terrible. Like, you can do it for like a 2x2 example, like just to see the mechanics, right? But normally you just don't want to do that, right? And then you'll end up with your lambdas, right? And then you can plug them back in here to find your eigenvectors, right? Those are your V's, and then you're good to go. Once you have the V's, then you can pick up the U's, right, via this equation here, right, AV1 over sigma 1, and you'll pick up your U's, and then you're good to go. You've got your singular value decomposition. But this is not in practice what you do. You would use something called the QR algorithm, for instance, or you can use something called Shor decomposition, which is what I prefer. And we'll have to do like another video on this, but the Shor decomposition really is, in my opinion, like as important a result as the SVD itself, to be honest with you. It's really good. Anyways, QR algorithm I think is probably the better way to see this, because we already have like all of the main pieces without having to extend this tutorial any further. And so what you need to do, right, you can numerically compute the eigenvalues of A transpose A or AA transpose, and it prevents you from having to like form this crazy characteristic polynomial we were talking about, right? And so how this works is like if we have A, we can do a QR decomposition. A is equal to QR. Q we've seen before is just an orthogonal matrix, right? Well, it's orthonormal because we have to normalize it, make them into unit vectors, times R, right? And R would, in this particular case, R is just Q transpose times A. So it's, if we knew what Q was, we can very easily compute R, so it's not a problem. Now how do we get the Q's though? Q's we can get from Gram-Schmidt. So this is a really nice part. But an actual program like Julia or MATLAB might just use something like Shor decomposition, or, right, it'll do the QR decomposition, but it might do it with something else, by like Gibbons rotations, or I actually don't know Gibbons rotations, to be honest with you. But I do know householder transformations. Like I never bothered to look into Gibbons rotations because I just prefer householder transformations, but maybe the other one's better, right? But never really looked into that, to be honest with you. But you can like look that up if you want to. Point is, how QR decomposition works like this, right? B sub k is equal to, right, Q sub k, R sub k, like this. We need a new page already? Come on. Okay. No, we lost that. Okay. Anyways, point being, bk plus 1, to get the next iteration, right? You take the current iteration, and you multiply by your orthonormal basis here, qk. Right, and you iteratively run this. And so you find your orthonormal basis for bk plus 1 at this particular point, right, with Gram-Schmidt. And then what you would do, after you've computed this for your first step, right, you would run the same thing again. So bk plus 2, and we'll just go for the next step just so you can see that iterative process, would just be bk plus 1, right, times qk plus 1. Right, fairly simple stuff. That's not b, that's r, I'm sorry. This is r. qk plus 1. This is an r, guys, I'm sorry. It's rk plus 1. Okay, right, and I hope you see why we're doing that rk plus 1 as well. Okay, and so this is the QR algorithm. So effectively what you're doing, if you think about this, is you're rotating, or it's a unitary transformation. Anytime you have an orthonormal matrix, it's a unitary transformation. And you're trying to align this thing, right, with its eigenvectors. So the matrix, right, so the matrix is going to become diagonal. And so this is like scaling, it's like some scaling factor along your principal axis. Like if you think about it, like go back to principal axis theorem, right? We had this Q lambda, Q transpose perfect factorization. And then yes, we're trying to get there, like as best as we can. And so that's how we're going to pick up these lambdas, right? That's how we're going to diagonalize the matrix. We're going to iteratively rotate, right, until we get to the directions of the principal axis, I guess is what I'm trying to say. So I hope I wasn't too convoluted on what I was trying to say here. And so suppose we started with bk, right? Some matrix bk, that would be, for instance, your original A transpose A, right? Then yes, that's your bk. And then so what you would do is then you would say qk times rk, right? So q you get from Gram-Schmidt or Householder transformations, or however you want to get it, and then you multiply that by r. And we said before then that we can get r by multiplying q transpose, which is very easy to do, times a, right? Very easy to, and I hope you can see where that came from. All we did really is we had a equals qr, and then we just multiplied, we left multiplied, right, by q transpose to get rid of the q, right? Let me just show you that. A equals to QR. I realize sometimes I'm just talking and I just assume you're following, but maybe you're not following, right? So I should just like, we're left multiplying here by q transpose to knock out this q. And so what we end up with is, right, q transpose, right, times A is equal to r, which is quite literally what we have here. So we have the r now, we can plug it in here, right, and we find what bk is, right, your kth iteration. And then we said before now, then to go to the next step, right, bk plus 1, this is the next step now, bk plus 1, the next step would be r sub k, right, times q sub k, right? So you just take this product here and you run iteratively, and then you do q k plus 1, r k plus 1, and then okay, you repeat over and over again. You just repeat this. So I think that's enough for me, actually. But yeah, that's just about everything I think you would need to know about singular value decomposition. You can actually use it to solve things like least squares. You can use it in robotics. You can use it in data science. Oh, it's used like everywhere, man. So I think it is like the climax of linear algebra. So most linear algebra courses would just stop there at the singular value decomposition, and so I will too. From here, I think maybe I'll start focusing more on my robotics project as well. Of course, I'll still be doing like videos in and out here or there, but more so focused towards my robotics projects. I have my FPGA that came in recently, so I need to build another CPU. Oh my god, how many CPUs am I gonna build? Anyway, I need to build another one, and we'll see where that takes us. In particular, I want to use that FPGA to program a 3D printed 6 degree of freedom robotic arm. And obviously all of these algorithms that I've shown you here are going to be implemented in hardware, which is probably one of the harder things, but I need to like squeeze every bit of performance I can, because I do not want to go spend how much ever it would cost to get an actual industrial arm. So we're gonna have to try and get like the cheapest solution we can. Alright, we're gonna call it end here. And the key takeaway from this video is don't gamble, guys. You saw what happened to me when I gambled at the beginning of the video, right? And then you just keep digging yourself quite literally a deeper hole. But okay.